This is part 2 of vector algebra practical calculations for game developers. We'll be looking at a slightly more complicated exercise this time. Two space fighters are taking part in a space combat game. The fighter A, currently at the position 2-2, as shown in the picture, is heading towards the destination at -714 with speed of 2 UPS. UPS stands for units per second, and this is its target displacement vector. The fighter B, currently at the position 012, is heading towards the destination at -16 with speed of 1 UPS, and this is its displacement vector. The question is, will the spaceship B cross the course of the spaceship A within 5 seconds of flight? So if the spaceship B is located here and it is flying along the blue vector in this direction, is it going to cross the course of the spaceship A, the red line, within 5 seconds of the flight? To find it out, we need a series of calculations for the fighter A and consequently for the fighter B. First of all, we'll calculate the target displacement vector, which is shown here as the red arrow. So displacement of the spaceship A can be found as the subtraction of the initial position 2-2 from the target position -714. The result is shown here, it's -912. Once we have target displacement vector, we can calculate its length, which provides the information about the distance the spaceship A has to the destination point. That's the square root of the first coordinate squared, which is -9, and -9 squared is 81, not -81, plus the second coordinate squared, which is 144. The result is a square root of 225, which is 15. Once we have the target displacement, uppercase dA, and its length, which is also the distance towards the destination point, lowercase dA, we can calculate the normalized direction vector, which is the vector pointing towards the same direction as the displacement vector, so it's pointing towards the destination point of the fighter A, but the normalized vector is a unitary vector, so its length is always 1. Such a vector can be calculated as the displacement vector divided by its length, or the distance to the target, so -912 divided by 15, and the result is shown here. The final thing to calculate in this section is the velocity vector for the fighter A, which is the normalized vector multiplied by the speed of the spaceship. So this is the vector pointing towards the same direction, towards the destination point of the fighter A, but the length of this vector is equal to the value of the speed, which is 2 in this case, and a straightforward calculation is the normalized direction vector multiplied by the speed of 2, and the result is visible here. This is the only result that we will subsequently use, so let's wipe out all the other calculations and just copy the VA value for the future use. Now we will repeat the same calculations for the spaceship B. So target displacement, the blue vector, it's the target coordinates of the spaceship B minus its initial position 012, and here is the result. Then we calculate the length of this vector, which is the destination, the distance to the destination for the fighter B, and it's 12 in this case. The third thing to calculate is the normalized direction vector, which is a unitary vector pointing towards the spaceship B destination point, and here it is. And finally, we will find the velocity vector for the fighter B, which is the direction normalized vector multiplied by the value of the speed, which is 1 in this case. So both vectors, direction and velocity, have the same value. And once again, we just need velocity vector, so everything else will be wiped. And we have two velocities, one of the fighter A, one of the fighter B. So, what is the position of the fighter B after 5 seconds? So we know the initial position of B, it's 0, 12, but what's going on after 5 seconds? So where is it going to be in the 5th second of the flight? To find it out, we can use the motion equation, which for any given point of time, t, provides the position of the moving object as a starting position, p0, plus vt, where v is the velocity, in this case it will be the velocity of the fighter B, and t is that time. So let's apply this formula to the fighter B and the 5 seconds time. So the position of the fighter B, which I just marked here as B5, is the initial position of the fighter B0, it's 0, 12, plus velocity of the fighter B multiplied by time. So B0, it's 0, 12, time is 5 seconds, and the velocity B has been just calculated as minus 0.8, minus 0.6. Here is the calculation. This vector multiplied by 5, it's minus 0.8 times 5 is minus 4, minus 0.6 times 5 is minus 3, 0.12 plus minus 4 minus 3, it's minus 4, 9. So that's the position of the fighter B after 5 seconds of flight. B5, that's another important value which will now join the other two that we already have. So we have velocity vector for the fighter A, velocity vector for the fighter B, the position of the fighter B at 5 seconds, and we also have the position of the fighter B at the initial moment, at the time 0, which is exactly this value rewritten from the text of the exercise. With these 4 values, we are ready for the final approach to this solution. Check which side of my course, it means the fighter A's, which side of my course the B is at its current position, B0, which is here, and at its position in 5 seconds from now, B5. So imagine I am sitting here in the fighter A, and I can imagine the position of the fighter B in time equals 0 and the position of the fighter B in time of 5 seconds. One is here, the other is here. I have to determine whether these two vectors are on two different sides of my velocity vector or at one side. As you may remember from the first part of this presentation, this kind of a problem is solved using a cross product, but firstly we have to calculate the displacement vector for both B0 and B5. So displacement for B0, I will call it D0, displacement at the time 0. It's B0, the position of the fighter, initial position of the fighter B, minus the current position of the fighter A. So it's 0, 12, minus 2, 2, it's minus 2, 10. Now I am ready to calculate the cross product. The cross product of the velocity of the fighter A and the displacement vector for the time equal 0. Velocity A is taken from here, minus 1 to 1.6, and the displacement at the time 0 has just been calculated, it's minus 2, 10. The cross product of vectors is calculated as multiplication or product of these two external positions, so x from the first and y from the second vector, so it's minus 1.2 times 10. This cross here means a multiplication of numbers, not vectors. Minus multiplication or product of the inner numbers, 1.6 and minus 2. So it's minus 12 from here, minus 3.2. Two minuses give a plus, so it's minus 12 plus 3.2, it's minus 8.8. It's a negative number. It's not that important that it's a negative number. We will rather compare the signs at the end of this exercise. But actually, in this case, the negative number means that the initial position of the fighter B is on the right-hand side of the course of the fighter A. Now we will do the same calculation for the position of the fighter B at the 5th second of the flight. So first, the displacement after 5 seconds is B5, the displacement here, minus A, minus initial position of the fighter A. And here we could actually use the position of the fighter A after 5 seconds, so it would be A5. It would be, in theory, a more proper solution, but in fact, if you think about it, it doesn't matter because wherever we take the current position of A or the position of A after 5 seconds, it doesn't affect the solution. The solution in terms of the only thing they ask here is about the position of the B fighter in relation to the course of the A fighter. This course doesn't change after 5 seconds or in any time in the future, so it doesn't matter if I take the initial position of the fighter A or the position of the fighter A perhaps after 5 seconds. The result will be exactly the same, and of course we are saving one calculation. There's one calculation less to do, so if it guarantees the same good result, why not to use this opportunity? So the displacement, going back to this place here, the displacement is between the B5, the position of the fighter B after 5 seconds, and the initial position of the fighter A, which is minus 6, 7. And the last calculation is the cross product. The cross product of the velocity of the fighter A, the red vector here, and d5, the displacement of the position of the fighter B after 5 seconds of flight. So once again, the velocity is calculated and it is available here as minus 1.2, 1.6, and minus 6, 7 is the displacement which we have just calculated. This number times this number equals minus 8.4, and the inner multiplication gives us minus 9.6, with minus in the formula for the cross product. Minus and minus gives plus, so the result is 1.2. Comparing both results, both cross product values, We can easily find that in the time 0 it was a negative number, and in the time 5 it's a positive number. Therefore, the fighter B, will cross the course of the fighter A. We can answer this even more precisely. Initially, in the time 0, the fighter B was on the right-hand side of the spaceship A, and after 5 seconds it was on the left-hand side of this spaceship. Thank you very much for your attention.